Well, measure theory, as it is taught in various courses, is often presented as a very dry subject without any motivation. I am trying to remedy that situation by providing an intuitive introduction to the subject. Consider these three examples. I have a length 2 cm and the same line continues for 3 more centimeters. My question is then what is going to be the total length, and the answer is 2 plus 3, 5 centimeters. Now I do the same thing with area. Here is an area 2 square centimeter and here is another 3 square centimeters. If I put them side by side like this without any overlap, then what will be the total area? The answer is again 2 plus 3, 5 square centimeter. The same thing about weight. This is a 2 kilogram and this is a 3 kilogram weight. I put them together on a weight machine. Then what should be the reading? It will be 5 kilograms. Thus, in all these cases, we see that we are adding them up. And this is true for length, for area, for weight, true for volume, true for masses, and true for many other things. Now, all these things have one common property, namely they are trying to measure something. Measuring a length, measuring an area, measuring a weight, and there are some other types of measurements also that we are going to see in a moment. Now suppose I have got two sets. This set has got how many elements? 1, 2, 3, 4, 5, and this has got 6 elements. 1, 2, 3, 4, 5, 6. What is the size of the union? Well, in this case, you will surely not do 5 plus 6, but instead you will do 5 plus 6, but then see that these two have been double counted, so we will subtract that. Now let's look at lengths. Again the same story. I have this long stick. From here to here it is 5 centimeter. From here to here it is 6 centimeter. There is some overlap which is 2 centimeter long. So what is the total length? Again the same story, 5 plus 6, but because of the overlap, I subtract the 2. And similarly, you can think of an example of like this in case of area. So this is also another way of measuring it. So if I measure length, if I count something, measure the weight, measure the mass, volume, all these things satisfy certain common properties, and that is precisely the story of measure theory. So all sorts of measurements satisfy certain common properties. Studying those properties in an abstract way is about measure theory. Much like metric theory, which has to do with measurement of distances. All types of distances, we call it in a single terminology, namely metric. Similarly here, all sorts of measurements, length, counting number, weight, etc., they come under measure theory. Since measurement is something that we do every day, so there are certain properties that we expect from any measurement. For example, if this is some object and you try to measure it in whatever sense, its area, its volume, or its weight, maybe it's a set, in which case you will just count the things, whatever, then you will naturally expect that if I take one part of it, so if it is made out of cardboard, you just take out this part. If it is a set, then it's a subset. If it is a three-dimensional object, then you take a lump out of it. Then whatever measure you are talking of, the measure for this should be less than measure for that, less than or equal to measure for that. Say you are talking about set, then the size of a subset should be less than or equal to size of the whole set. So this is one of the obvious properties. We already saw another obvious property. If I have one thing and another thing, there is no overlap, it has some measure and it has some measure, then the measure should add up. If it is length, length should add up. Count of a finite set, that should add up, whatever. So these are the obvious properties. Now whenever there are so many obvious properties, it sometimes is seen that some property will follow from other properties. So people are interested in finding out the smallest possible list of such properties, so that all other obvious properties are basically consequences of that. So I am going to write down such a list. Well, the first property is what I started the lecture with. If you have certain disjoint sets, I use the term set in it as a generic way. It could be length, it could be an object whose area you are trying to measure, volume, whatever. They're disjoint, no overlap. With measure, you replace the word measure by length or area or count, whatever you like. Call them alpha 1, alpha 2, etc. Then you take the union. Then it's measure, the same measure. If you are using count here, use count here. Length, then length. Should be sum of the alpha i's. And this sum could be infinite, that is countably infinitely many things, could be finite, I do not care. So that is the first property. Now here is another property. Whatever measure you are talking about, that should better be greater than or equal to 0. You are measuring size of something. It's an object with negative size, doesn't sound nice, so we put the very natural thing like measure is greater than or equal to 0. If I say something has got negative area, you feel uncomfortable with that. So these are the two main things that we expect all property, so all types of measurements that should allow. Now, just from this description, it may not seem anything very nice or anything very tricky here. It is just obvious kind of thing. Why do I need a theory for these obvious things? Well, the point is, pretty soon you will see that even this simple thing will run into certain problems. And that is something that we shall discuss in the next video.